Warning: sodium is a dangerous reactive metal. Para-chlorophenyl and dioxane are carcinogenic. Wear gloves and work outside in a fume hood. Methanol is flammable and reactions with sodium are fire hazards. Fire safety protocols must be in place. Greetings, fellow nerds. I finally got to the next step of pyrimethamine synthesis to work, so in this video we're going to make 2-para-chlorophenyl 3-oxopentane nitrile. This is step 5 of the pyrimethamine synthesis. First, we start with 300 ml of methanol dried and distilled from molecular sieves 3A as I've shown in a previous video. Set up on top a reflux condenser. Now get 15 grams of sodium metal. I showed how to make this in a previous video using magnesium, sodium hydroxide, and dioxane. Links are in the video description. Cut and roll the sodium into wires like this so you can drop them to the condenser. Now one by one drop them in with the cooling water turned on. Don't drop in too much at once or the bubbling will go out of control. Drop in a piece at a time and let the bubbling get back under control before dropping in more. What we're doing is reacting sodium with methanol to make sodium ethoxide while generating hydrogen gas. In a previous video I show you can also make sodium ethoxide by reacting sodium hydroxide and methanol and then removing the water with molecular sieves. That method is much slower than using sodium metal, but much safer since it never overheats. Adding sodium to methanol is dangerous in that it can get so hot that it catches fire. Considering that methanol and hydrogen gas are both highly flammable, this can go very bad very quickly. Nonetheless, because this is a very fast and clean method, it's the preferred method in most laboratories. You also don't get contamination by molecular sieve dust that can be a problem for some reactions. Eventually, all the sodium will react and will have a solution of sodium ethoxide and methanol. Now reassemble your reflux apparatus into a distillation apparatus and distill off the methanol. We want relatively solvent-free sodium ethoxide for the next step. The reason why we start with excess methanol rather than stoichiometric is because solid sodium ethoxide can precipitate out. This blocks further reaction, so it's almost impossible to perfectly react sodium and methanol in a 1:1 ratio. So we add excess methanol and then remove it by distillation. Don't discard this distilled methanol. It's still pure and also water-free, which is useful for upcoming videos where we'll need it again. Now the final amount of methanol is very hard to boil off, so put a shroud around the flask and increase heating to around 250 Celsius. Keep heating until no more methanol distills over. You can tell when you see the distillate temperature start dropping. Now turn off the heating, stopper the flask, and let it cool. We want to minimize the amount of moisture that gets into our sodium ethoxide. While it's cooling, we can prepare our reagents. Get 30 grams of para-chlorophenyl acetonitrile that we made in a previous video. Then add in 30 milliliters of ethyl propionate that we also made in a previous video. All links are in the video description. Shake it up until everything is dissolved. Now with the cooled sodium methoxide, add the reagents. Now add enough dioxane so the total volume is about 300 milliliters. We made dioxane in a previous video from sulfuric acid and antifreeze and dried it using sodium magnesium oxide aggregate. Now assemble a reflux condenser onto the flask again and gently heat until it starts refluxing. What we're doing is using the sodium methoxide to deprotonate the para-chlorophenyl acetonitrile and then react that with ethyl propionate to make 2-para-chlorophenyl 3-oxopentane nitrile. Looking back, I forgot to break up the cake of sodium ethoxide first, but eventually with enough stirring it'll break up on its own. Now as it runs it may foam up. Adjust heating and stirring to keep foaming under control, but try to keep it as hot as possible. Anyway, it's no secret I've been trying to do this reaction for the past 8 months and always failed. I even used exotic reagents like tetrahydrofuran and potassium t-butoxide, but I never got to work. I was almost ready to give it up when I posted my problems here on YouTube and a number of you saw right away what was causing my failures. I was working on too small a scale. Even without knowing my scale, you knew what the problem was. It was so much work to make para-chlorophenyl acetonitrile, I tried to conserve it by working on a small 300 mg scale. But for condensation type reactions like this, small scale tends to hurt the process. Stray water from the air and walls of the glassware can contaminate the reaction and stop it from working. Scaling up makes the reaction more reliable. This is one of those times in chemistry where size does matter. My performance problems for the past 8 months was because I wasn't large enough. If I had just taken the risk and used everything in one shot, this would have worked and I would have been done in January. Yeah, well, hindsight is perfect, as they say. I'd like to personally thank Hofsep for emailing me and walking through the problems I was encountering. Thanks. Anyway, keep heating for 2 to 3 hours. Then turn off the heating and let it cool. Now for the aqueous workup and washing, get a total of 1 liter of water and fill the reaction flask as much as you can. Mix it up with a glass stir rod and pour it out. Wash out the reaction mixture this way. I didn't just pour it out first because I found the mixture solidifies when cooled. Adding water first helps make it easier to work with. Once it's all in the beaker along with 1 liter of water, stir it for 10 minutes or so to thoroughly suspend the chemicals. Now add in 100 milliliters of 30% or 10 molar hydrochloric acid and keep stirring for another 10 minutes. Turn off the stirring and let it settle. What we're doing is neutralizing the sodium ethoxide to sodium chloride and methanol. The sodium chloride and methanol are very soluble in water and stay in solution while the organic products will precipitate out. Most of this is done in a few hours, but I'm going to let it go overnight. And here we are the next day. The organic layer on the bottom should have our product. Now pour off most of the water and use a separatory funnel to get the rest. I recommend washing the organic layer again with 100 milliliters or so of water for further purification. And here is our crude 2-p-chlorophenyl 3-oxopentane nitrile. I sent a sample off for NMR analysis and got back this spectrum. Over here are the symmetrical aromatic peaks. This peak over here is the chloroform D solvent peak since I asked the NMR lab to use chloroform D for the scan. This here is that one little proton on the trisubstituted carbon. It's heavily shifted downfield being connected to such strongly electron withdrawing groups like nitrile, ketone, and phenyl. This spike over here is leftover dioxane. It wasn't entirely washed out with water, but it's not going to affect our future chemistry, so it's not worth putting in additional effort to remove it. Now for the interesting part. This complex multiplet is the protons right beside the ketone, and this triplet is the protons at the end. This complex multiplet is characteristic of our target compound, and this is very strong evidence we were successful in making it. Now this broad peak over here is water. For obvious reasons, we have a lot of water contamination. Overall, this spectrum pretty much confirms that we have our desired product. Our yield is 41 grams or 99%. Now I don't think the actual synthesis is that good, especially for a garage level synthesis performed using ghetto quality reagents. The NMR spectrum shows numerous impurities like dioxane, and they're probably inflating our numbers. Literature yields for this procedure range from 50% to 70%, so I still think we're doing pretty well. I'm not going to bother to remove the impurities at this stage since we can remove them later in our next steps on our pyrimethamine synthesis. So there we have it. After 8 months, I finally got to the next step, and the holdup was all because I was working on too small a scale. As you can see, the reaction, while very involved, is actually not that hard, and if I had done it right the first time, I would have been done in January. Now well, better late than never, I guess. At this point, I wanted to thank you, my viewers, for believing in me and pushing me forward, even though I had essentially given up. I would have abandoned this if it weren't for you. Now at this point, we should check our map again and see where we are. We were converting para-chlorophenyl into 2-para-chlorophenyl 3-oxopentane nitrile, and have just cleared it. The last 8 months weren't a total wash though. We also had to make the solvent dioxane, so we can add that to our pathway as an unforeseen detour. Interestingly enough, we also figured out how to make sodium metal with domestically available chemicals. So even if we still totally fail in the upcoming steps, we can still say we made a new and useful discovery that justifies our research. Our next step is a reaction of 2-para-chlorophenyl 3-oxopentane nitrile with trimethyl orthoformate. But before that, I'm going to convert the rest of my para-chlorophenyl acetonitrile stock so I have a good amount to use in case I fail more in the future. And I need to make a video on preparing a guanidine salt. Hopefully we can finish this project before the end of the year. Thanks for watching. Special thank you to all of my supporters on Patreon for making these science videos possible with their donations and their direction. If you're not currently a patron but would like to support the continued production of science videos like this one, then check out my Patreon page here or in the video description. I really appreciate any and all support.